Está gravando. So just a few more minutes and then we can start.
Yeah, no problem.
And have you ever been in Recife, Luis?
Yes, but just passing because I love Brazil. I go every time I can, but and so to the north I have been several times. Usually the flights are either to Recife or Fortaleza. I've been in Fortaleza. I've been in Maragogi.
Oh, okay.
Very nice place. I love that place.
Yes, it's
and
beautiful.
then I go often to Rio de Janeiro, and
Cool.
I even stayed there for several months while I was doing my PhD. I was working with Caio Levenkopf in Rio, and so we had very nice time with Caio. I went to visit him a couple of times, and was very nice. This was a long time ago. And from time to time, I come back either for visiting people or for holidays. I love
He was already in Niterói, or when he was still in Rio?
No,
Rio
he was at UERJ at that time.
Right. Okay, yeah.
The second time he was, I don't know if officially or not, but he was at CBPF. And now he's in Niterói.
Yeah.
And yeah, so I like it a lot, but Brazil is too big. I have to go more often. I've been also to Minas Gerais, to a couple of places, but there's a lot still to see. It's huge.
That's true.
So I don't know if you know, but I'm originally from Argentina. I'm not from Chile.
Yeah, I guess this because of I was checking your CV and then I was like, okay, I think he's from Argentina.
Yes, I'm from Cordoba, from the center. And at some point, I just tunneled through the Andes and I appeared here.
Cool.
Yes.
There's a road that you can go, but it's quite dangerous, right?
It's nice. It's beautiful. It's not so bad. The last part is tough when you traverse the Andes properly, Aconcagua. But it's amazing. I mean, it's amazing. The lowest part where the road goes, it's at 3,500 meters, and you have Aconcagua on the side that is almost 7,000. So it's amazing. Actually, here where I'm sitting, we are very close to Aconcagua in the straight line, probably 70 kilometers. But it's not that fast to reach the border, because you have the mountains, and then you have to really somehow do a contour through, and it's quite close. It's quite close to the border. There are even some pictures of Santiago that no one believes, but they are real, that are taken from other mountains closer to the coast, that are lower mountains, where you can see Santiago, and in the background you can see Aconcagua.
Wow, okay.
From the city you cannot see it because it's too close, but if you get farther away and you use a powerful lens, you can see it. It's amazing.
Wow.
It's really amazing.
Okay. Well, I think we can start.
Great.
So, okay. Welcome, everybody. CJ will not be here today, so I will do the presentation of our speaker. So today we have Luis Torres, which is an associate professor of physics at the University of Chile. And before, he worked in Argentina as a professor and CONICET independent research scientist. He was also fellow of Alexander von Humboldt Foundation in Germany, in Dresden, working with Professor Giovanni Cuniberti. He was also working in France, in Grenoble, with Professor Stéphane Rocher. And he was also an associate in the International Center for Theoretical Physics in Trieste. So welcome, Luis Torres. Thank you very much for accepting our invitation. And yeah, the stage is yours.
Thanks a lot, Nadia. Thanks a lot, Luis, for the invitation. I'm very happy to see you in this format, and so I hope that you like the talk. So for everyone, I will just show very briefly because I'm mixing my own signal, and so you will not see a presentation really. But if you go to Google Meet, you can click on anyone. For example, I will click here, Nadia, this button, and then you pin that person, and so this person appears there immediately, and then this way you don't miss the presentation. So that's the way you can do it. And so thank you very much for the invitation. I'm working now at the University of Chile in Santiago, and the talk of today is going to be on topological states out of equilibrium. I will mention a bit the research we have been doing in what people call Floquet topological states, and also the search of topological states in non-Hermitian systems. That's something more recent that probably you have seen many papers. It's kind of trendy now, and so I will give a background on all this. So since I've seen that this is intended as a colloquium, I tried to make this quite general talk, and so I will give an introduction to topological states in condensed matter in general at the very beginning. So when you see this name topological states in different systems, it means something very special for people in condensed matter, and I will try to convey you that meaning in the following slides. So for this, I like this quote from Pauli, who said that God invented the bulk, the surface was invented by the devil. And so this quote by Pauli, who is famous for this kind of phrases, can put us in a kind of uncomfortable situation, especially if you work in 2D materials like me or Luis. Immediately you say, why? What's going on? We are working with physics of the devil. And so that's something that we have to really think about how to get out of this problem. So someone is complaining that they cannot see the presentation. So as I said a couple of minutes earlier, you have just to go to my profile here and pin using that symbol there, and then I will appear in first screen, and you will see everything. So let's continue. So as Pauli had this famous phrase that make us uncomfortable coming from 2D materials, and so how to get out of this problem? And I don't want for people to tell me that I'm doing physics from the devil. So we have to get out of this. On top, the big problem is that evidence seems to suggest that this is true. As you can see, the famous paper by Novoselov and Gaim, the very first paper had the mark of the devil there. It has the 666, so it seems that we are screwed. But no, there's a way out, and that way out comes thanks to this gentleman, Niels Bohr, who said that the opposite of a fact is a falsehood, but the opposite of one profound truth may be very well another profound truth. And so for him, this kind of reasoning that came clearly from inspired by quantum mechanics was a way of a source for creative inspiration. And so if we take this phrase by Niels Bohr, we can try to somehow mix up things to get in peace with our minds if we do 2D materials. And here what I will use is the fact that when we mean that the state is topological, what we are actually doing is connecting the bulk with the boundary. So we are connecting somehow these two things that seem to be opposite. So God with the devil, and to make this image even more tastier for you, I would use this analogy with one of these bonbons that probably you have tried. I like them a lot. I used to have other others that are similar from Marco, but here this is the Italian version. So you have this Ferrero Rocher bonbon. You have the inside that has one color, is light brown. The outside, it's this Nutella that is more consistence of a chocolate. And so when we are talking about, for example, topological insulators, typically we are thinking of a material that is a bit like one of these sweets. Inside you have something that it's an insulator. Outside you have this coating that is the topological states that will be bridging the gap, and so the difference with the topological insulator is that when you cut a topological insulator, you don't get the insulating part exposed like you have here in this suite. It's a bit like if in this bonbon you have the coating that is melting. So the moment when you cut, the coating melts, this chocolate melts and covers immediately the insulating part. So every time you cut this into pieces, you get let's say the topological states outside. So this, in this sense, it is different than this analogy. So this just to motivate the talk. So anyone with problems to see the presentation, please remember to pin my face in. Yes, you have just to pin.
No, it's okay, Luis. Just people are not used to it. It's fine.
Yeah. Sorry.
We are very conservative. We like to, keep things. But this is fine. It's quite great actually that we can see both you and the presentation. Great.
So before starting properly the talk, I would like to thank my collaborators. Here, just a short list of them, incomplete, but it's good to say thanks before starting. So for the things I'm going to talk about today, I'm especially thankful to Pablo, Virginia, Hernan, Stefan, Gonzalo, Carlos, Eric, Jose, and Victor Manuel, who was a student in your university, and I had the luck to meet him, and so we did some very nice works with him, and all the institutions that support us for funding throughout the years. I'm now sitting at the University of Chile. Well, right now I'm at home, but we used to sit at the University of Chile. These are some images of, we have a very nice new building, also an older one, where the physics department is sitting. It's a very nice place. It's very, very close to the Andes. So if any of you happen to come here at some point, please just drop me a line and I would be happy to host you here. So the outline of the talk is as follows. I will start with a brief introduction to topological insulators. So for this, I will start with integer quantum Hall effect and talk a bit about this boundary correspondence that I just mentioned. And then I will flash you through the search for topological states beyond equilibrium. That is some of the things I'm doing. And it's let's say a line of research that has less than a decade, and there has been a lot of developments in this, and so I hope that I can convey you the essence for this research. So this talk is kind of iceberg type talk. Essentially, most of the talk will be the background. So everything that goes at the beginning will be underneath the surface. It's all the background that we use for what we are doing today, and just towards the end, I will go towards the things that are newer and that are floating on top. So this is for the organization of this. So let's go to the first part, a brief introduction to topological insulators. This, I would say, first thing, it's for us, for me as condensed matter physicist, everything started with the integer quantum Hall effect. Before there was the classical Hall effect discovered by Edwin Hall in 1879. He was actually trying to, he was puzzled by something that Maxwell said and wanted to prove Maxwell wrong. And so he found that if you have a high magnetic field and you pass a current, just because of the Lorentz force, you get the carriers deflected towards the sides. So if you pass a current, you have a magnetic field, you generate a voltage that is perpendicular to that current, a Hall voltage. So 100 years later, this gentleman, Klaus von Klitzing, found that a completely different effect that's in the quantum regime, that is the integer quantum Hall effect. He was working on samples like the ones that are pictured here. That is very practical samples. They were actually devices. They were MOSFET devices. He was testing them at low temperatures in very high magnetic fields at the in Grenoble in February 1980. And it was around 2 a.m. in the morning when he saw something that was completely unexpected. These samples were essentially practical devices, so they didn't have controlled impurities or anything. And what he observed, to his surprise and of all of the community, was that if you have a setup like this one, so he had a 2D electron gas, so the electrons were confined in such a way that they were moving in 2D effectively. Now you can think of graphene, but at that time it wasn't that easy. And so they managed to have a 2D electron gas. They had a high magnetic field, and you have a source, a drain, and what they measure is the Hall voltage here. And with this Hall voltage and the current, you can compute the Hall conductance. This conductance associated to this perpendicular voltage. And instead of seeing what classically you would expect, that is this green line here, what they saw, it's this is as a function of the occupation of the levels. What he saw was this black line, where you have these plateaus that are very, very strong, very pronounced, and very precise. He realized immediately that these plateaus were integer multiples of E squared over H, up to many significant digits, 7 or 8 at that moment. And so he immediately realized this because he had a background, luckily, he had a background in metrology. And immediately he realized that, wow, this is strikingly precise in different samples that were, as I said, with uncontrolled impurities. So this was really a tough thing. And immediately a lot of people tried to understand why this is so. And so this work was worth a Nobel Prize in Physics a few years later for him, and many other things that I will mention in a second. A way to understand this effect, it's as you can see sometimes in the courses in quantum mechanics, you see this example where they tell you you have a 2D electron gas, you put now a high magnetic field, you can compute the so-called Landau levels. So if the magnetic field is strong enough, what you see is that the system, the spectrum becomes discrete. And so you have these red lines here that are discrete, highly degenerate, corresponding to different of these, skipping these orbits that you have here, these closed orbits. And so essentially what you have is that you have no transport in your system because the electrons are just looping around. And so you will not be able to move from one place to the other, at least in the bulk of the system. And so this is in the presence of a high magnetic field. So now what happens is that as soon as you have borders, edges, what happens is that essentially the bulk of your material is, as I said, is essentially an insulator. But at the edges, you have these skipping orbits. Essentially, you have incomplete orbits, as you can see here. I will make them a bit bigger. Let's see if this lets me. No. So you have these skipping orbits here at the edges. So you will have states that really move through the edges, and they will move as shown here by the arrows. So the bulk will be an insulator, and through the edges, you will be able to move but as if the edge was kind of one-way street. So in this edge, you will have states that only move in one direction. In the opposite edge, you will have states that move in the opposite direction. So this is what is called, you have chiral states. And because of this, there's something very important that happens, that is, suppose that I want to disturb this perfect plateau. So to disturb this perfect plateaus in the whole conductance, what I would need to generate is backscattering. So I would need somehow to, for some of these electrons that are getting in, to bring them back to the electrode where they came from. But since the edges behave as one-way streets, the only way to have this backscattering would be in the plot I showed you before. Here would be, for example, if I get from the source inside the sample, I would have to choose this edge, because this is the only edge where I have states that propagate from source to the right. And if I want to have backscattering, the only way would be to really switch sides to the opposite edge and then come back. But as I told you before, the bulk of the system, all this part inside, behaves as an insulator. Therefore, to pass from one edge to the other, you have to do essentially a tunnel effect through the insulator. And this is something that is exponentially forbidden. And so this is the reason why it's very difficult to generate backscattering. And essentially, these plateaus are so precise. This is a view from the edge of why these things are like that. But something even more interesting comes when you get to understand this from different side, a topological side. And this is precisely what Dowles did. He managed to prove that the whole conductance can be written in terms of the very phase over 2 pi. The very phase is what is called a topological invariant. It's an object that is an integral over k space, the space of labels of your states, of the wave functions for the bulk. So at the end, the property of the bulk will be able to tell you the magnitude of your whole conductance. And so this property is somehow, it's very surprising. And this is a manifestation of what people in this field call the bulk boundary correspondence. So this means that the bulk of the system, so the properties of the system very deep inside, far from any terminations or surfaces, rules what happens at the boundary, at the surface, at the edge of your material. And so the bulk will tell you if you have a given number of edge states and what's the number of them, independently of the atomic details of the boundary. So this is very deep, because it's very different from what we do in several huge research lines in material science, that is to look for ways of functionalizing materials. This is very different. In this generation of materials with topological properties, this is something that doesn't happen. And essentially because you tie this object that is a topological invariant, that is essentially imagined as an integral that counts a number of knots in a given shape, or number of holes in a given shape. This can only be an integer. You cannot have a shape that has a fractional number of holes. And so this is the kind of property that will be connected to what happens at the interface or at the edge of the system. So at the end, what we get to understand from this is that not all insulators are equal. So until, let's say, 1980s, we were thinking that we had insulators, we had metals. If the gap was small, we called it a semiconductor. Now we get to know that there are some systems that behave differently. Within the group of insulators, there are some that are different. And so we have topological insulators and normal insulators. So here I'm representing a normal insulator with this shape, a topological insulator with this one on the right. So the only way to transform one into another is to cut this, this shape. And in such a case, I have a topological invariant, a number of nodes in this case that is not well defined. This is what happens for a metal. So this is a hand-waving way to understand how the boundary between a topological and a non-topological material, like here, I will surely have states that are metallic, because the only way to pass from one shape to the other is to cut it and have the number of nodes that is not well defined, as it happens in a metal. So as I said before, this becomes a paradigm that is very different from what people is used in material science. For example, if I have a normal insulator, it's a topologically trivial insulator, typically, as in this plot, the piece of the material is here in blue. And so I have a band structure composed of bulk states that are in gray and surface states that are in green. And so this is energy, this is K. And so this is here the chemical potential. And so I have surface states, bulk states. So one of the things that people do a lot, and it has been very successful up to now, is that you can somehow put molecules on the surface, somehow functionalize your material to add new properties. And when you do this, like in this plot here, for example, here you have a lot of tile molecules that get attached to your surface. You essentially change the properties of the material. Your surface states change a lot. You can even pass from a situation where you had states available to one where you had no states available. And of course, the chemical potential changes because you are adding or subtracting charge. So this for sure changes substantially. But now if I play the same game with the topological insulator, what will happen is that the surface states will hardly get modified at all, but most likely the only thing I will get is just a shift in the chemical potential because I'm adding or subtracting charge. And this happens because the surface states in topological insulators are robust. And so they do not depend on these details, atomic details of determination to exist. So it's the bulk who is ruling those properties, and that's why they are not affected. And so this is an important message that we get from this, and this is in a more modern view. But at that time, at the time of the integer quantum Hall effect, it was not clear at all that I could do this as a property of the material. I needed the magnetic field until this gentleman here, Haldane, realized in a famous paper now in 1988, although at the beginning very few people could understand this paper and cited this paper, he realized that you could play some games to get physics very similar to the one you have in the integer quantum Hall effect, but now as a property of the lattice. And so he formulated a model that is called Haldane model. And this model, well, as I said, this paper at the very beginning, no one saw it. Only after 2006, it started to be cited. And well, this by now it's a kind of it's a kind of classic. The moment when I took this screenshot, casually the number of citations also had the mark of the beast. So you see 3666, and so what he proposed was essentially a model for graphene with an additional term. So graphene, that at that time didn't exist, was already very much studied in theory, and he decided to add an additional term. That's what we call today Haldane's term. So besides a staggering potential, so a change in the on-site energies between the two sublattices in graphene, he proposed a term that was between second nearest neighbors, these arrows that you see here, and this term had to be complex. And if you had a phase in this hopping between second nearest neighbors in the correct way, then he showed that you could have very much a system that is gapped, like in this plot here, and a line traversing this gap, bridging this gap, that corresponds to states that are edge states propagating here through the edge of the sample. So somehow similar to what we had in the integer quantum Hall effect, but the big difference is that now this occurs as an intrinsic property of the lattice. he invented this term that he couldn't give a physical reality at that time. But if this term was present, then you could have this sort of strange insulator that has edge states bridging the gap. So what's an example somehow of this sort of system? The problem with this is that this type of term that he invented at that time doesn't appear in nature, and so this delayed things a lot. So as I showed you, this famous paper was 1988. He got the Nobel Prize in 2016 for it, and it took a long time until 2005, when these two guys, Kane and Mele, published this famous paper. By now was 2005. To put it into context, it's 1 year after graphene got isolated, so after the famous paper by Geim and Novoselov. And so they were somehow thinking of graphene now as a concrete material, as something that you could get in the lab. And so they said something striking. They said, if we consider graphene with a strong spin-orbit coupling, then this spin-orbit coupling will induce this sort of physics similar to the one that Haldane had, with some differences that I will show now. But now this appears as a very, very physical term. So what happens in this case is essentially that in their model they add spin-orbit coupling. And so this spin-orbit coupling can be understood very simple terms. You think that you have the electron around the nucleus. So if you sit in the reference frame of the electron, then you see the nucleus that is moving around the electron. And so as such, it will produce a current and the magnetic field that will couple to the magnetic moment of the electron. So this will lead to a coupling, and that is the spin-orbit coupling. And this is the form that mathematically this term has. And what they realize is that essentially by adding this spin-orbit coupling that in principle is present in all materials with to different extents of strength, but it's present there, what you get is a Haldane model for each spin component of your graphene with spin-orbit coupling. So for one spin component, you get a Haldane model with a given chirality for the edge states. For the opposite spin, you have the opposite chirality. So at the end of the day, what you get is states that are, like in this plot that I'm showing here, states that are counter-propagating. States with spin up move in one direction along one edge, and the ones with opposite spin move in the opposite direction along the same edge, and the opposite on the other edge of the sample. So at the end of the day, you have something that is very similar, even more interesting than Haldane's model, out of a physical interaction that is spin-orbit interaction. Unfortunately, their model, their estimation for the strength of spin-orbit coupling in graphene was a couple of orders of magnitude too high. Spin-orbit coupling will be stronger the heavier the element. Carbon is quite light, and the spin-orbit coupling is not that strong. So at the end of the day, this effect was not observable in graphene directly. And but they had a message that was very strong. Their message said that besides realizing this physics similar to the one in Haldane's case, but now with spin, the states were very robust, and the states that were observed were very robust, and the reasoning was very deep, because imagine you have two edge states moving on opposite directions at the same edge. So now you'd say, oh, but in your previous argument, you said that the problem was that to produce backscattering, you had to move from one edge to the opposite. And so this required tunneling, and this was very hard. But now at the same edge, you have counter-propagating states. So what does protect these states from backscattering then? And the answer, the very non-trivial answer that they gave in this paper, is that what really protects these states is time reversal symmetry. If your Hamiltonian has time reversal symmetry, so it commutes with the time reversal operator T here, then what happens is that you can prove in a couple of lines that I will just skip here, that there's no way to connect these two counter-propagating states if your Hamiltonian preserves time reversal symmetry. And this is something that can be done in 3 lines, but the consequences are very deep. They mean that these states will be really robust in this system. And so at that time, it was a theoretical prediction, but then a couple of refinements and further proposals brought this to experiments in 2007. So the first realization of topological insulator appeared in 2007 with this paper by Molenkamp's group that is very well known by now. And so the people started to talk about a new state of quantum matter and really exciting times. So with this, I have given a very, very brief and broad overview of what is topological states. This is the first part of the talk. So I hope that from this part, you take a couple of key messages. First, the gap has a key role because it's crucial in this protection. There's this strange phenomenon of bulk boundary correspondence that connects what happens deep inside the sample with what will happen at the boundaries, at the edges. And so this is kind of non-local strange thing that appears in these materials, and it's part of the game. For modern topological insulators, spin orbit coupling is the key interaction that we are looking at. So now you can feel excited when you hear this phrase that something it's topological. So, but this has already a couple of years, and people keep expanding the frontiers and thinking how to go to the next thing. And so this reminds me a lot of these old maps, like in this one, where you try to really map what's going on. And sometimes when you do this, you make a lot of mistakes, like saying that this is the map of the whole world, like in this one, and well, soon after you realize that you have just seen a little bit of the thing, and then you get in trouble with strange creatures, as you see there. So I would say that the first part, the integer quantum Hall effect that I described, has to do with somehow the mainland. Then as you get out from solid land, you start to see stranger things, like quantum spin Hall effect, topological insulators, and if you go deeper, you have several smaller places where to go, like Floquet topological insulators that I'm going to talk about right now, and also topological states in non-Hermitian systems. That is kind of a more recent trend. So these Floquet things appear quite frequently in the literature, and one of the questions that motivate all these people, especially coming from materials, is if we can make of any material a topological material by using light. And so the idea is, for example, if we could endow graphene with topological states, this would be great, because you could have a lot of nice properties in a material that is broadly available and that we know how to process very well. And so this is one of the motivations for trying to go out of equilibrium to generate these states. And one of the ways, as I mentioned, it's using light. As I mentioned today, one can use magnetic field, one can use spin orbit coupling for topological insulators. Another way would be to think of going out of equilibrium and using a strong laser illumination. And so then you have these, what that people call Floquet topological insulators. These are, for me, the two founding papers, one by Oka and Naoki, and another one by Lindner, that appeared already a couple of years ago. The general idea is to try to use light as a topological switch. Essentially, you turn on your laser and you change these very deep and internal properties of a material, like behaving like an insulator or topological insulator by now playing with strong laser illumination. So this is the general idea. Let me continue. So from where does this name Floquet come from? Well, it appears because Floquet theory is the more widespread theory, the prevalent framework for dealing with these laser illuminated systems. Essentially, you model these systems as a system with a time periodic perturbation in a semi-classical approximation, and then you have to deal with this somehow. In quantum mechanics, dealing with time-dependent Hamiltonians is not that easy, but if the dependence is periodic in time, then you can do some games, and this is the Floquet picture in just 2 slides. What you have is that that essentially you get an effective equation that is very much like the equation, time-independent Schrödinger equation, but now for a different set of states and with a different Hamiltonian. The picture is the one that I'm showing here. It's like, suppose you have graphene, it's illuminated. Then initially I have a model that is like this honeycomb lattice here. Now, thanks to this laser illumination with a clear frequency, what I have now is the possibility of having, for example, one state with a given number of photons, the same state with +1 photon excitation or -1 photon excitation with respect to that reference. And so essentially what you are solving, it's a problem in a space of replicas. You have your original space and all the replicas. And so at the end of the day, what you have, it's a problem in a higher dimensional space that appears because you are solving a problem of electrons plus photons. So long time ago, we were doing some theory for this, and we realized that if you do this for illuminated graphene, one would have gaps appearing in graphene, as I'm showing here. This is time average density of states as a function of energy. If you apply strong illumination, you will have effectively, without laser, you have the gray lines, so you have just a cone. But now, if you have a strong laser illumination, you would have gaps in this composed band structure of graphene. And this is something that we predicted a long time ago with Hernán Calvo, who is there in the picture. And this was at that time for us very interesting. We realized that the sweet spot for doing this in the lab would be the mid-infrared. So that's why the scale you see here corresponds to h bar omega, the photon energy on the order of 100 milli-electron volts. That is laser in the mid-infrared is where you could do this in the lab. We did a lot of theory for this, and we tried to convince many experimentalists to do it. It was very difficult. And then something appeared from an unexpected place. A group at MIT did the experiments not in graphene, but at the surface of a 3-dimensional topological insulator. The surface states of a 3-dimensional topological insulator are very much like graphene. You have a conical dispersion relation with a bit more of curvature, but very similar. And what they observed using angular resolve photoemission spectroscopy is they observed these sidebands that appear because of Floquet theory in the system, and they were able to generate a gap if the polarization was the correct one. So for us, this was quite surprising. This appeared at the end of 2013. Then there were more experiments that were becoming better and better every time. So at that point, our question was, well, we see that we can get something very special. We can just, by illuminating a material, we can change its properties and from a metal to an insulator. And now the question was, could we make it a topological insulator, or is it a normal insulator or a topological insulator, what we are getting? And for this, what we did was some heavy numerics at that time, and realized that effectively, if you look at the band structure of graphene, you produce some gaps, and you could see states bridging the gap. These states moved like in the arrows here, so they moved like like chiral states, like in the integer quantum Hall effect. So effectively, what we were having was kind of Floquet topological insulator in graphene illuminated by circular polarization. So this was interesting at that time, but the next question that was driving us forward was what happens with the Hall conductance. As I mentioned at the beginning, if you have these chiral states, then you'd expect to have a Hall response. And then the question was, will there be a Hall response also induced by light in this system, similar to the integer quantum Hall effect? What will be the differences? And this is something that we addressed later by using an atomistic simulation of a system that is illuminated in a central part and with all the leads that you could have in a Hall setup. And we realized using these Floquet techniques that effectively you could see a rough plateau in the Hall conductance, but this plateau would not correspond exactly to the number of edge states. There are many edge states that are not excited. Only a subset of them become excited and contribute to this laser-induced Hall effect. Something that was imagined for observing these gaps. It was very difficult, not observing graphene for many years. Observing a Hall response requires doing a transport setup is even more difficult. So we were sure that these experiments were going to be very difficult, that there was a need of someone special to carry them out. But finally, they appeared this year in Nature Physics. This is a group in Hamburg. We knew that we needed a special guy to do this. We thought of this MacGyver, but instead we got this one. This is MacGyver. And so this guy managed to do these very tough experiments. And so what they observed is, here you have the dispersion. And so they observed, here, this is the Hall conductance. They observed a plateau. And this plateau got very close to 2e square over h, as we were predicting when the intensities were strong enough. And so this is very good news, because it means that this physics has passed at least one experimental test. And we hope that there will be many more experiments in the coming years on this area. And so so this is for this part on using light as a topological switch. I try to convey you that we can change the topology of both ordinary materials, metals, or semiconductors by using light. And I showed you some of the differences. There are a lot of things that people are actually right now talking about, and we have put many of these things together in a special article, the Quantum Materials Roadmap 2020, that it's appearing now in Journal of Physics Materials. It's already available in a preview version. So you can see there some of the perspectives that we wrote together with James MacGyver for this area of non-equilibrium systems, but you have a general view on all the area of quantum materials. So there are many things that people are doing now, like, for example, trying to get to emergent phenomena, but by using light. So try to use the self-response of the system to drive new phenomena. It's really a very exciting area. We have made a lot of publications on this over the last years. You can check them in my website. But now I want to use the last 5 minutes that I may have to briefly flash you on a different area that has to do with the search of topological states in what people call non-Hermitian systems. So that is other of the areas that I mentioned before. So probably you have seen during the last years a lot of research appearing with the keywords non-Hermitian in the title all over. Many papers appearing over the last years, some experimental papers, some theory papers. The first 2 years were only theory papers, and then you started to see more and more experiments with quite crazy claims. And well, this area is what people call today the area of topological states in non-Hermitian systems. Why these non-Hermitian systems are interesting? If you have done a quantum mechanics course, probably one of the first things they told you is that Hamiltonians need to be Hermitian in order to have real eigenvalues. Well, if your Hamiltonian turns out to be non-Hermitian, you could have imaginary eigenvalues. The imaginary part essentially takes into account the possibility of having a finite lifetime, and so it will not be really stationary states. And this is something that it's relevant in many situations. For example, typically non-Hermitian Hamiltonians as effective Hamiltonians are ubiquitous. For all of us that have been doing quantum transport, we have been dealing all the time with effective non-Hermitian Hamiltonians due to interaction with the leads and interactions eventually with electrons, with phonons. And so normally you end up dealing with effective Hamiltonian that is non-Hermitian. And there's also, for example, if you want to describe to the very simplest level electron-electron and electron-phonon interactions, the simplest thing that you can do is to add self-energy that has takes into account the lifetime because of this interaction. So immediately you have also a non-Hermitian description. And besides, in photonics, mechanical experiments, it's very natural to also have effective Hamiltonians that are non-Hermitian. So at the end of the day, you could think that actually non-Hermitian Hamiltonians are a better approximation to what really happens in reality, even in materials, when you take into account electron-electron and electron-phonon interactions. And then you can say, well, all the theory we have is for Hermitian Hamiltonians. What happens in this situation that might be even more realistic? And so this is where a lot of people became interested in during the last years. So I started to look for non-Hermitian states for topological states in non-Hermitian lattices. And here there were a lot of challenges. If you look in YouTube, you will find another full talk on this topic that I gave a couple of months ago, so you can check it. So by now, for now, what I will do is just mention one result that was very surprising for us, is that suppose you have a lattice that is pristine, so you have no disorder. So if you come like me thinking of materials, you say, well, if I have an ordered lattice, then I have no localization at all for the states. If the lattice is pristine, then I should not have localization. I should have states in the bands that are moving throughout the lattice. Well, in a non-Hermitian system, what could happen is that even a pristine lattice may have all the states localized at the boundary. So this was quite shocking for us the first time we found it, something that we found with Victor Manuel, that was a student from your university. And that was quite surprising. And this is something that people today call it the non-Hermitian skin effect, because all the states move there. And so that's something that's very interesting, and that has been studied over the last few years and realized experimentally, for example, in robotic metamaterials, in the quantum dynamics of different systems, in topoelectrical circuits, in funneling of light, and so really very different systems. And so I invite you to check the other talk to have a better idea. And so by now I will conclude with this topic, and thank you for your attention.
Okay, thank you, Luis, for the very nice talk. So first, I would like to ask my colleagues to open their microphones to thank Luis.
Questions?
Yes, and now we are open for questions. I don't know, I haven't checked the chat. Well, okay, I have one question.
Sure.
I couldn't understand, you said like when you were explaining the Floquet observation, why do you need a very strong laser or a light field? Why do you need, does it need to be strong?
Yes, this is a very, very good question. Actually, what we realized at the beginning when we saw that it was possible to open a gap by shining a laser, we said, well, there has been a ton of experiments in Raman spectroscopy where they are doing this all the time. Why they didn't see any consequence there? Then we started computing and we realized that for the typical intensities that you have for the laser frequencies in Raman spectroscopy, the effect is really negligible. It's very, very small because h bar omega is huge, so you need huge intensities also to be able to really excite these photons. And then what we realize is that as soon as you lower the frequency, at some point you may do it with an intensity that is smaller, but if you make the frequency too small, then you have a problem that is all this physics occurs over a scale that is h bar omega. If h bar omega is on the order of smaller of temperature, then you will not observe anything. So at the in between, there will be an optimal point, and this happens for the mid-infrared when you have the wavelength is 10 microns more or less, and h bar omega is on the order of 100 milli-electron volts. So it's much less than the around 2 electron volts that you have for the visible.
Okay.
And so that's a bit the reason. And so you don't only need a strong laser, you also need to go to the right frequency if you want to see it without destroying the material. So it's really an effect of strong light-matter interaction.
Okay, cool. Thanks. Any other question? Mateus, if you want, you can open your microphone, or you are... Okay. So Mateus Sarmento is asking, please speak concerning the role of material impurities on the turning on-off of the topological states.
What's the role of impurities?
Yeah,
Yes. Oh, defect. Yeah, it's a very good question. In principle, one would think, wow, impurities can really destroy this picture. But the elegant and nice point of topological insulators is that this state of the material itself and the topological states that appear bridging the gap are robust to impurities and things. So the fact that it's robust to these impurities allows you to really ignore them, at least for a broad range of concentrations. Of course, if the concentration is very strong, then the full thing gets destroyed, but there's a broad range of concentrations where really they are not playing a role because the properties of this material are dictated by what happens in the bulk. And so there, it's a pristine bulk of the system, and at the end of the day, you have something that is robust.
Cool.
I have a technical question. So Luis, when you showed your the graphene and the state with the plus or minus 1 photon or plus or minus 2 photon, so you have the Floquet Hamiltonian for that. What exactly is the extra term? How does this photon added or missing enters your Green's function?
Sure, it's a very good question. Let me come back to one of these pictures that I have here. Let me see. Here, for example, what happens now is that you will have terms connecting these replicas, and these terms that connect these replicas essentially are the transitions, the possibility that you have to transition from a state with a 1 electron in one side with a given number of photons and emit a photon or absorb a photon and move. And so you can pass from one side to the other, absorbing or emitting photons. And so these terms essentially come from the vector potential in the Hamiltonian. You have, let me see if I have here a slide for this. So all this is done in a semi-classical approximation. And let me see if I have here a slide with the Hamiltonian. So what you do is if you are using, for example, KP approximation, long wavelength approximation, what you have is that if you have a term that goes with k, now k gets shifted by E over C times the vector potential. And so the vector potential depends on time. And so this gets into the Hamiltonian. And now when you do Floquet, essentially you do a Fourier thing for this. And so now the different Fourier components will give you these hopping terms to emit or absorb photons. This is what enters now in this Floquet picture. So at the end of the day, now if you start with the 2D material, you end up thinking in 3D with a lot of layers and the connections between the layers. And this is something that we are trying to exploit a lot, because during many years we were thinking really in 3D materials because of this Floquet stuff and the interactions between layers.
Can you control the position of the gaps?
Yes, the position of the gaps, that's something that I didn't explain, appear exactly, look. The scheme is as, thanks for the question. If I have graphene and I have no radiation and I look at 1k direction, I have the cone. Now, if I add the radiation, what happens is that I have one cone for each replica, and they are shifted among themselves by h bar omega, the photon energy. And so now what happens is that you have these crossings between the different cones that appear if you look just half the way between one Dirac point and the next one that are shifted in h bar omega. So at the end of the day, these gaps will appear at plus minus h bar omega over 2, and so they move with the frequency of the laser.
And it works in all materials with this type of cone in the electronic structure?
The three-dimensional topological insulators, for example, it happens, the physics is the same, the surface states also have the cones, and that's where they observe this for the first time.
Mm-hmm. Right.
That's something that at the moment we didn't expect.
Okay.
I think there are a few more questions.
Yeah, we have one question from Professor Antonio Azevedo. Can you comment on magnetic impurities or magnetic proximity effect on the breaking the time reversal symmetry in Dirac materials?
I think the question is related with at the beginning I mentioned topological insulators and the work by Kane and Mele that is very famous. And I said that you have these counter-propagating states, and that these counter-propagating states are protected by time reversal symmetry. Magnetic impurities break time reversal symmetry, and as such will allow for you to flip the spin and get backscattering through the same edge. And so they are the kind of impurities that break the robustness of these topological states in topological insulators.
Okay, Antonio, I don't know if he answered your question, but if not, you can write and I can read it. Okay, we have another comment. Mateus, do you want to make your comment? You open your microphone. Oh. Yeah, no, we cannot hear you.
No.
No. Okay, so Mateus is commenting, I would like to address the possibility of impurities as a further mechanism besides light, as a factor for changing the region of stability of each strange creature you find in your ocean.
Good comment. Okay. Yes. There are actually, you can see there's now some interesting trend of trying to get topological states out of disorder. And actually, Kyle Levenkov has a very nice recent work on this, where they try to get topological states in system just by adding a lot of disorder. And so the technical problem to deal with this is big, because you lose Bloch, you know, and once you lose your translational symmetry, it's complicated. But you can check. Kyle Levenkov has a very recent work on this with the people in Sao Paulo, I think. It's very, very nice work on amorphous systems.
Cool. Okay. So any further questions? Okay, then if not, I would like to thank our speaker again.
Thanks to you.
Yeah, I think we can open our microphones again, no?
Nice. Nice, thank you.
Okay, Luis, thank you very much. It was very nice. Thank you.
Oh, thanks to you. I'm very, very happy.
Yeah, maybe next time we can have you here in Recife.
Would be great. Would be great. And please, if you happen to come around anywhere around, just write a few lines. I would be happy to host you.
Yeah, cool. Thank you. Okay, guys. Bom final de semana.
Bom final de semana.
See you. Ciao.
Ciao. Thanks a lot, Luis, for the invitation, and Nadia.